Hello, physicists. Welcome to our first lab for heating. Sorry, just need to set up the mouse when we get to the lab part. Look, for our first lab for heating, today we are going to look at the idea of proportionality, and we're going to specifically do that by looking at, well, what happens to the rate of heating when we change the masses of the water? How does it look like on the graph when we're heating it? Now, I do understand that the glare on this is a little bit high. It's mostly going to be for my referencing, and so I will point it out to you a little bit and talk about what I'm seeing. This file for Sparkvue will be available on eLearn so that you can go and download it now if you wanted to and have a reference for it. So let's talk about the apparatus here. I have a heating plate. I'll just turn that up a little bit higher so it keeps heating up. And I'm going to set it to about a 3. I preheated it. One thing to keep in mind, if you were doing anything with heating in your very first trial, you've started off a cold hot plate. Your second trial, if you want it to be a fair test, it needs to be a cold hot plate. And secondly, if you are heating off of a cold hot plate, then the amount of heat energy that whatever you're heating is not going to be consistent. I also have 2 thermometers over here. I have a Sparkvue digital thermometer that we're going to hook up, that I have hooked up to that, or I will hook up to that. In fact, I'm probably going to need to reset that because it's turned itself off. Oh no, it's still on, great. And a basic old analog alcohol thermometer like the ones that you've used in class. I have 2 prepared beakers. They're the same shape. It's fairly important because if the glass is a different amount or the surface area that's going to be in contact is a different amount, that's going to cause some errors and inconsistencies. However, one has 50 ml of water and one has 100 ml of water. And so we're going to see just what happens over a few minutes of time. I've got a stopwatch here so I can call out, say every 15 seconds, what the temperature is on our analog. So let's turn this down to about, was it set? All the way up to 4. All right, so let's put it at 4. Bring my thing over. I will need to just drop these a little bit to prep them. Now, our Sparkvue thermometer is set here to record about every 2 seconds. I didn't want to make it a rapid fast. We get a lot of noise happening in it during that. Hopefully that's not too high. That's too high. No, that's just caused a little bit of error, unfortunately. I'll reset those. Resetting beakers, thankfully, is not terribly difficult because we can just run some water in it and cool it down. I'll re-put 50 ml of water in that in a little bit. Let's just use this until we get our right height. That needs to be just a touch long. That needs to be just a touch long, but otherwise it's okay. Lovely. Now, the reason that's important is we want to be able to just lift it up, place it in, have it ready to go immediately so that we can see only the effect of the heating on our temperature. Now, I'll just pop out of frame for a second so I can hit start on Sparkvue. There we can see it's gathering temperature. The ambient temperature near the thing is about 24.3 25-ish degrees and dropping a little bit. I'll grab my stopwatch, and this is why we always tell you, do these things in groups of 2 or 3 so that you can have multiple people doing things at the same time. That's on, that's in, that's started. And I'll just read off the temperature every 15 seconds. It started at about 25 degrees though. We can see there's a big drop here as it initially went water. You can just barely see it there. 15 seconds, that is reading at about 25. Meanwhile, this is reading a little bit below 25, so there's probably still some catch up there that the thermometer is doing. 30 degrees now, we're up to 28. And again, yeah, this is pretty close. There will be some differences. Now, as we look at this here, we can see that this general trend, you know, is looking reasonably linear, not perfect, but never is. 31 degrees at 45. And now, just make sure that's fully immersed. It's fully immersed, good. And then there's this sort of weird dip that happens, and it'll happen again. Sorry, I did miss the 1 minute, but now at 1:15 it is 38. So it's gone up, 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 then it's dipped, up, dipped a little bit. We'll see that often with these things. I'm also going to do a recording one on doing phase changes today, and we'll see something similar. At 1:30 it was about 42. And that's because heating is not a perfect situation. 1:45, it's 44. It is a statistical thing. We'll talk about what that means in a minute. 2 minutes. We are at 46. And what that means is that while the bottom is getting hotter, the top of the water is not the same temperature as the bottom of the water. The probe, you know, is testing a region of the space, 49 at 2:15. You see it's linearizing out a little bit more. Got a little bump there, little dip there, little bump there. But generally what we're looking for here is what's the pattern, what's the trend. At 2:30 we are at 52 degrees. We'll stop it at about 3 minutes. 2:45, it is at 54 degrees. In fact, seems to be catching it. And it's leveling off a little bit here. Now, it may very well be that because this is about the limit of how hot the hot plate is, but it's still continuing up. And at 3 minutes, we're at about 58-ish. Now, I'm just going to leave that to run. I'm not going to read out any more of these while we do that. I'll just do 3 minutes of timing. So let's leave that to run just while we talk for a second. So thermodynamics is what we call a statistical science, or I mean, all science is technically statistical, but it's really important to understand this. In here is billions to trillions of atoms. While the thermometer is saying that right now it is 61 degrees Celsius on that probe, there are some atoms near that that are not 61 degrees. It's weird. There are some atoms in here that are hotter than 61 degrees. There are some atoms in there that are colder than 61 degrees. Remember, when we say temperature, what we're really talking about is how much kinetic energy the particles have. So while there is a non-zero probability, I'll just draw it out. Now, I might not be able to see this too well. We can just see it. You may be familiar with the shape from grade 10 probability and statistics called a bell curve. When the temperature was 61 degrees, what it was really sort of saying here is that it seems on average, the middle point, I've drawn a line there, I've written the number 61 underneath it. 61 degrees is the average temperature, and that's what our probe is reporting to us. We see it's continuing on nice and linear as well there. We're up to into the 70, just hitting the 70-degree mark there, but we can see it's a nice linear line. Talk about what that means in a second. Now, this bell curve, I don't know what the standard deviation is for temperature, to be honest. I don't know if it changes based off the number of atoms you have or what the material is. But let's just say that the standard deviation is, let's say 0.5 degrees. So 0.5 degrees Celsius. So that means somewhere in this middle region, I believe it's about 67% of it would be as low as 60.5 degrees Celsius up to as high as 61.5 degrees Celsius. So the temperature can vary a bit, right? But then you've got into the next region up to about 95% would be plus or minus 2 standard deviations, so 1 degree Celsius. And then within 99% is 1.5 degrees Celsius. Notice 99, even if it's 99.9%, is not 100%. There is a non-zero chance there's an atom in there that has a temperature or kinetic energy that equals the temperature of 100 degrees Celsius. There is a non-zero chance that it could be higher, though at that point it would be trying to breaking free of its nearby friends and transitioning into a gas. Conversely, there would also be some that would be a lot colder. So this is what I mean by statistical. That's why we see these little bumps and dips, and why we need to take a long range so that as the liquid moves around, because you'll learn, think about a bit convection, you learned that in grade 9, is that as we're heating that liquid, the temperature of the liquid at the bottom causes it to rise, and the cold liquid at the top causes it to fall. And so you've got this cold and warm liquid moving around near the thermometers, and so the analog just doesn't have the sensitivity to pick it up, but the digital thermometer certainly does. Okay, so I will stop that. Probably should have got some tongs over there in the thing for the moment. So let's talk about what proportionality means. Proportionality means that as one thing increases, another thing increases by the same proportion. If we double one thing, something else doubles. Ignoring the fact that you tend to get sales and there's the whole, like there's a minimum cost. Actually, let's just use McDonald's as an example. I'm going to buy every student in the class a packet of large fries. The more students that I have, the more money I need to spend, because every student needs a packet of large fries on their own. I believe this year we have 23, so there'll be 23 packets of large fries, and you can look up what the cost of the large fries is. But if half of you drop out, then I have to spend half as much money. If somehow we double the number of kids in the class, which wouldn't work because the maximum is 25, I think, then I'd have to double the amount of money. Okay, so proportionality is a connection between what the one value and another value and how they relate to each other. I will just turn off Sparkvue as well. Obviously, when you're looking at this data, that big long drop in the pink there for run 3 is when I took it off the thing. I'll try to annotate that a little bit as well for you so that when you're looking at it, you can see what's going on. Now, so we see here a proportionality between energy, because you've learned about energy. This is obviously giving off heat energy. It's quite warm over the top of it, quite warm when you're near it as well. So this is giving off some amount of heat energy. It gives off the same amount of heat energy, or at least as close to the same as possible. You may see this orange light popping on and off a little bit as it heats up, and then it realizes it's reached its maximum temperature, so it turns itself off for a second, starts to cool down a little bit, then gets too cold, then heats up again. So it's as close to constant as possible. A Bunsen burner can be slightly more erratic, which is why I'm using a hot plate compared to a Bunsen. But the longer we leave it, the more energy it gives off, and it gives off a steady amount of energy.
So when we go back to here, if I go here from 100 seconds to 200 seconds, so at 100-second duration, it gave off some amount of energy. If I then double that proportion, I go, okay, 200 seconds worth of energy, okay, it's given off twice as much energy. So therefore, we can look at, well, from 100 to 200, the temperature change went from about 37-ish to about 57-ish. So let's say about 20 degrees. But we go from 100 to 300 seconds, it went from 35 about 70-ish. So it didn't quite double the difference there. That's only a difference of 35 compared to a difference of 20 from before, though that is some quick rough math. So it'll be closer than, and the scale isn't great there. So it'll be closer than what it seems, 20 compared to 15. There's also some other things going on, and I'd ask you to think about, well, why is the amount of heat energy, the temperature in the beaker not being doubled, even though the time it's being receiving energy is doubled? Because it should be doubled. And if we go from 100 to 400, lucky I left it to 400, that's triple the amount of time. Well, that went up to about 82 degrees. And again, so that's just a difference of another 12. So you can see there, that's not perfectly linear. That is curving off somewhat. There's a reason for the curve. You should try to think about, well, what might be curving? Because if you're going to do any sort of practical on heat as the basis for your student experiment, that will be useful to keep in mind. Anyway, talked a lot. Let's do our second trial now. But this time we are doing 50 ml of water. So we are halving the mass. We are keeping the same amount of energy. Okay, so this thing is still going to give off the same amount. However, the mass of water that we are heating is now half as much. We activate Sparkvue, our next run, and I'll just leave the third run off for a second. And we are a go. That's not resetting. Now, it looks really small in comparison because it's still zoomed up for the previous scale. That's been about 15, that's at 28. What I will do is I will turn, actually I won't, I'll leave it there. We'll do it when we get to a minute. 30 seconds is about 32. What I will do as well is I'll edit Sparkvue a little bit just to change the names of these runs and annotate it a little bit to make it easy for you to read. At 45 seconds, we were at 37. Screen's flashing a bit. Sorry, 1 minute, we were at 43. We can see it is progressing up at a reasonably steady line. You should be able to just see it. This color's a little bit darker, so it's a bit better. So 115, it is at 48. $130, it is at 52. $145, it is at 56. Well, I can get to 3 minutes at this rate, because you can see that we're passing 60 already. 2 minutes, it is 61. And so based off that, the analog is a little bit behind the Sparkvue. The Sparkvue is more accurate. 215, it is 66. It's about 2 degrees behind. They are at the same depth as well, and I try to keep them to the same radius from the center. 230, we're at 70. $245, we're at 74. And then we'll stop this stopwatch at 3 minutes. It's also pretty close to the same maximum temperature as before. 3 minutes, we are at 78. All right, so I'll just leave that to keep running while I talk for a second. Have a look at this. Just make a prediction in your head for a second. Think about, well, how's the steepness of this gradient going to compare to the previous run? What do you think it's going to look like? Do keep in mind, obviously, we didn't start things at the exact same time each time, so we can't just go, oh, well, because this one started later, the gradient is going to be less. That's not what we're comparing here. We just want to compare the steepness of things. So let's turn on our run 3. And we've hit 4 minutes, so that's been running for about 200 seconds. We'll leave it there because it's at 90, it's close to boiling. And I'll just turn that off. And I can hear the bubbling starting. Okay, so if we look at our graph, and if you can't quite see the graph contrast well, please download the Sparkvue file from eLearn and take a look at it there. I will annotate the one for you so it'll be a bit easy for you to find what I'm pointing at. Even though we only turned this on, well, we only immersed it probably a difference of, what's that, 10-ish, 15 seconds compared to when I hit start on the screen. And this one did start at a bit of a higher temperature because the thermometer was still a bit warm, though it did drop to about 24. The previous run started at about 24 and dropped down about 1 degree or so in the water. So the initial starting temperatures were not identical. We can see here, or at least when they equalized them, you can see here that run 4 is a lot steeper than run 3. So we had less mass, we have the same amount of energy, but the temperature increased faster. We had a higher change in temperature. If we were just to look at, say, a 50-second window here of heating, let's go 100 to 150, we can see here it goes from about 50 degrees to about 66 degrees. So what's that difference of 16? While here, from 100 to 150, it goes from 37 to about 47, so about 9-10 degrees. Okay, so half as much mass, nearly twice as much change in temperature. So again, we're dealing with a proportionality, a linear proportionality. Okay, the amount of mass affects what the temperature change is, but in this case, it affects it the other way. So when we double one thing, the other thing drops down. So it's inversely proportional. It's not linearly proportional. So this is the end of our first prac talking about proportionality. The Sparkvue data will be there available for you to investigate a little bit closer, and we will talk about it in class as well. Have a great day. Talk to you later.